All right, welcome everyone to the IQIM seminar. We're lucky to have Eugene with us today to talk about black holes and their robust encodings. So there's going to be two ways to ask questions like in previous weeks. You can either write in the question and answer section of the Zoom your question, and then I will try to read it out to Eugene, or Eugene, if you look at that while you're speaking, you should try to read the question so that the recording can capture the question. And then secondly, if you want to speak, you can raise your hand, and then Angelo or I will try to give you speaking permission. And then you can interact with Eugene over your question. So yeah, that's it. And without further ado, I'll hand it over to Eugene.
Great, thank you, Alex. It's always great to be at the IQIM seminar. So today I'm going to talk about some work that I did with Isaac Kim and John Preskill, which is available here in the archive preprint. And I'm going to talk about robust encodings of the black hole interior, and in particular, one way of addressing this so-called firewall paradox, which is sort of very prevalent in the high energy community right now. And before we do anything else, the first thing we should address is what exactly the firewall problem is. And since we're going to be talking about black holes, so the first thing we should talk about is sort of the life cycle of a black hole. So let's consider, for example, initial matter, which is in a pure state. So here, for example, we have a blue shell of, I guess, photons, which over time, so time always runs upwards for us, over time starts collapsing inwards on itself. And as the photon shell collapses, these outgoing light rays start becoming deflected. And as the shell becomes more and more dense with time, the deflection of the light rays become increasingly angular until it eventually becomes trapped inside an event horizon. So these marginal rays that become deflected exactly sort of at the boundary of being trapped and not trapped forms this event horizon, and eventually a singularity forms, and we have the birth of a black hole. So initially people thought that black holes just sit there and don't do much. But nowadays, we know that black holes don't just merely sit stationary after their birth. So black holes emit radiation, Hawking radiation. And through this radiation, they slowly but steadily, they waste away. And the presence of Hawking radiation can be understood in many ways. But a very simple conceptual toy model is through pair creation at the near event horizon region. So you can think of heuristically as the quantum fluctuations at the near event horizon region being amplified by the stretching of space-time in this region. And so you have pair creation at this region, and this consists of a maximally entangled pair, one of which is outgoing, that forms the Hawking radiation, and another one which falls in towards the singularity, forming a part of the black hole interior. So this is a very simple, very conceptual toy model of black hole evaporation. And our goal is now to try and make this a bit more quantitative. And if you'll trust me that, yes. So if you'll trust me that—
Robert just joined the, but you keep going.
Okay, all right, yeah. So if you'll trust me that this is a salient model of black hole evaporation, we can see that there are some immediate problems that start to arise when we start to conceptualize this toy picture. So how can we make this, this picture of pair creation a bit more quantitative? So let's start with some pure state, which on some initial time slice represents the overall state of the black hole. So this would be this pure state psi m here. And through this Hawking evaporation toy model, at every time slice, Hawking radiation starts being induced from pair creation. And this suggests that we should model our time evolution by updating our initial matter distribution with these EPR pairs representing the outgoing mode B and the infalling mode B tilde. Because we expect the radiation process to take place at the near event horizon region, the matter distribution itself is not altered very much by locality. So we're going to keep this matter distribution either the same or very slightly unchanged. And the actual form of this matter is not going to be relevant to us because we're going to be mainly interested in the radiation part of this state. So if we continue our time evolution, then we repeatedly add on these EPR pairs. So after n time steps, after n of these pairs have been created, we can sort of model our Hawking radiation as a state which is just n copies of this maximally entangled pair. So remember, we always have one pair, one mode, which is outgoing, which we always call B, and one mode, which is infalling, which we call B tilde. So I haven't justified why this is an accurate picture for Hawking radiation. And without going into too much detail, I cannot justify why. But I hope you'll trust me that this does give an accurate representation, at least for our purposes, of what black hole radiation looks like. And I'll just mention now that, in fact, it's necessary, it's essentially necessary for the outgoing mode to be maximally entangled with the infalling mode, because you can show that the structure of the quantum vacuum at the event horizon needs this kind of structure for the space-time there to be smooth and for the equivalence principle to hold. So now, if we look at the previous states, and you can imagine tracing away all the interior modes and just looking at the reduced density matrix on the outside. And you'll find that tracing away all the interior modes and perhaps this matter distribution, you're left with just the maximally mixed state on the exterior. And this is just the old famous result that the Hawking radiation appears to be a perfectly thermal state. But this is rather problematic because if evaporation continues until the black hole is completely radiated away, then you're left with a purely mixed state, or purely mixed state is a bad word, you're with a completely mixed state, purified by nothing because the evaporation of the black hole has been completed. And so you start with initial states of pure matter that collapse into a black hole, and you end up after evaporation with a completely mixed state. And this violates the unitarity of quantum mechanics. And so this is sort of the paradox that Hawking was initially confronted with, and this is the traditional black hole information paradox. And the black hole information paradox is essentially an asymptotic statement. It concerns the state of the black hole at its very initial beginnings and its very end at asymptotically late times, that pure states evolve into mixed states. But you can sort of sharpen the argument to finite times using entanglement entropy arguments. And this would give us the modern formulation of the black hole information problem, which is called the firewall problem. So to see exactly what the firewall problem is, we're going to separate the state of the black hole at some time into three distinct parts. So we're going to fix a late outgoing mode, sufficiently late outgoing mode, and we're going to label this by some large integer k. So this is the kth mode which has been emitted by the black hole, if you will. So as we argued before, there should be some infalling mode here which purifies it. And we're going to denote the collection of all the modes emitted before this k as E, the early radiation. So we separate the black hole into three parts. We have an infalling mode, a late outgoing mode, together with the early radiation E. So from the toy model before, and as argued for the smoothness of the horizon, we know that the outgoing mode must be maximally entangled with its partner modes inside the interior. And if it's maximally entangled and in a pure state, we expect that the entanglement entropy of this pair to either be exactly zero or very close to being zero. And so this gives us our first relation, which signifies the smoothness of the event horizon. But if we also trust in quantum mechanics, we expect the overall time evolution to be unitary. And so because we start with a pure state, we expect to end in a pure state, which means that at sufficiently late times, these outgoing modes must start to purify this maximally mixed early radiation. So if we take K to be sufficiently large, if we take the mode to be of sufficiently late times, we expect the outgoing modes to start purifying the early radiation to maintain unitarity. And this means that at some point, it must be that the collective state of BK together with E is more pure than just the radiation by itself. So this gives us a second entropy relation that signifies the unitarity of quantum mechanics. So we have one for the smoothness of the horizon and one for the unitarity of quantum mechanics. And altogether, we have three relations now. So we just have the regular strong subadditivity of entanglement entropy, which must hold for any tripartite state. We have the entropy relation given to us by smooth horizons, and the entropy relation given to us by the unitarity of time evolution. And unfortunately, these three conditions are actually contradictory. So if we just begin with the sum of the entropies of this late outgoing mode together with the early radiation, just using the fact that this is zero together with the regular subadditivity of entropy, we can conclude that this is equal to this relation here. So now we can apply strong subadditivity to get this inequality. But we know that this part here is just zero. So all we're left here is the entropy of the exterior radiation as a whole. And by the unitarity postulate, this must be less than the entropy of the early radiation by itself. And this gives us a contradiction now, because from this, we conclude that the entropy of the late outgoing mode must be strictly negative, which is not possible. So this formulation of the black hole information problem is called the firewall paradox. And the reason why it's called the firewall paradox is because out of all of these mutually contradictory statements, the original authors of the firewall paradox thought that the most acceptable solution was the breakdown of the smoothness of the horizon. So basically, equation 6 here. They thought that maybe entanglement was broken at the horizon, and there exists some kind of energetic curtain at the horizon due to this entanglement breaking that just burns up everything that tries to enter the black hole. So this is the firewall paradox in a nutshell. And with all paradoxes, right after its conception, there has been numerous proposals for its solution. So there's many proposed solutions to the firewall paradox. I'm not even going to attempt to summarize all of the possible ways that people thought that this was or was not a problem. But we will focus on one particular proposal, which in some sense is the simplest, the most naive solution you can think of, but also in a sense, the most confusing one. And this is a proposal which is called B tilde in E. So let's distill what exactly is the gist of the firewall problem. And the basic problem with the firewall paradox is the following. You have an outgoing mode B, which must be entangled with both an interior mode B tilde and the early radiation E. And this causes a violation of the monogamy of entanglement. But if monogamy is our fundamental problem, then there's a very naive, very simple solution, which is to simply identify the two problematic subsystems. If B must be entangled with both B tilde and E, then why don't we just postulate the fact that the partner interior mode B tilde is actually somehow encoded within the exterior radiation E? This would solve the monogamy problem. But of course, this is much easier said than done, because at face value, this appears to cause many more problems than it appears to solve. For example, if the interior is actually embedded within the exterior, how can such an embedding respect the causal structure of the black hole? Because ostensibly, the exterior radiation should be space-like separated from the interior. On a similar note, how do we protect the interior from outside observers? If the interior was encoded inside the exterior, then external agent should be able to manipulate the outside radiation, but at the same time, they should not be able to access the interior mode. Otherwise, that would be very problematic for us. It would enable causal violations and all sorts of problems. Not to mention, Interstellar would not be nearly as exciting if they didn't have to jump into the black hole to do what they did. And there's the practical problem of how can such an embedding be realized in the first place? What is it about black holes? What particular properties of black holes allow such an embedding to be present and unproblematic, I guess? So we're going to spend the rest of this talk. So this is the problem we're trying to address. And we're going to spend the rest of this talk talking about an information theoretic resolution, a proposal for making this B tilde in E proposal conceptually concrete and unproblematic. So I'll just mention that this B tilde in E proposal has spawned or motivated a number of related proposals. And there is actually a fair amount of evidence for its validity inside holography and inside these black hole physics in general. So for example, you may have heard of these ER equals EPR proposals, or these recent entanglement islands conjecture. And in a sense, these are all related to this initial B and E proposal. So we want to now take a look at this proposal through an information theoretic and quantum computational lens. And this is a summary of what we're going to do, essentially. So we're going to postulate that black holes are efficient scramblers in a very precise way. Namely, we're going to argue that the exterior Hawking radiation emitted by a black hole is in what's called a computationally pseudorandom state. Now, I'll explain exactly what I mean by computationally pseudorandom in a bit, but we're going to argue that this is the key property that allows this proposal to work. Through this pseudorandomness hypothesis, we're going to show that black holes define a natural encoding of each of these interior modes B tilde into the exterior Hawking radiation. And that moreover, such an encoding forms a natural error correcting code, which protects against all the operations that an exterior agent can apply, so long as they have sufficiently small quantum computational complexity. And by small complexity here, I mean small with respect to the entropy of the remaining black hole. So physically speaking, not very small at all, just small compared to the systems we're looking at. And the takeaway message here is that a sufficiently powerful observer can in fact detect violations of causality and locality, perhaps. But this is only provided that they're able to perform operations which are of exponential complexity in the entropy of the remaining black hole. And we're going to argue that this is just not physical for realistic observers. So before moving on, let's talk a bit about what it means for something to be pseudorandom. So we say that a quantum state rho here is computationally pseudorandom if it is effectively indistinguishable from the maximally mixed state. So I've denoted by sigma here the maximally mixed state with respect to all algorithms of sufficiently small computational complexity. So in this case, algorithms which are polynomial time in the system size. So if any algorithm accepts rho with essentially the same probability as it accepts the maximally mixed state, up to some small error, which is typically exponentially small, then we say that the state rho is computationally pseudorandom. It appears maximally mixed. And it's a priori not clear if these pseudorandom states even exist, but they do, and they actually exist in great abundance. And there's a very simple counting argument that shows this, which basically boils down to the fact that there are too many states to be distinguished and not enough low complexity circuits to be able to distinguish them all. So in fact, if you take a random quantum state sampled from the Haar measure, for example, then with overwhelming probability, that state is actually going to be computationally pseudorandom. You can sharpen this argument a little bit. So for example, this is a theorem in this paper here by Fernando Brandão and Aram Harrow and Horodici, and they look at two value POVMs with complexity less than some polynomial, some n to the k for some integer k. And they show that essentially for all n qubit states with circuit complexity less than some slightly larger polynomial, that these states will be indistinguishable from the maximally mixed states with respect to these POVMs up to an error of at most exponentially small, so 2 to the minus n over 4. And so this shows that, you know, we do have these computationally pseudorandom states, but in a sense that this notion of pseudorandomness from the gerundicity of the state is not really enough for our purposes, because we don't expect the black hole state to be a state which is Haar random. Haar random states are not efficiently preparable. And we do expect black hole states to be efficiently preparable because black hole formation and black hole evaporation is an efficient process. It takes place on the order of n to the entropy to the 3/2 or something like that. So it's actually a very small polynomial on the entropy. So a black hole cannot be pseudorandom by virtue of being Haar random. Black hole evaporation is efficient. So for pseudorandom states to be useful to us, we have to argue that they can be efficiently generated. And this is a bit harder, but it turns out that this is also doable. So if you assume standard cryptographic primitives, in particular the existence of quantum secure one-way functions, it can be shown that there exists efficiently computable and still pseudorandom states, states which are preparable in polynomial time, but not distinguishable from the maximum mixed state in polynomial time. And this was shown in this paper by Ji and Liu and Song. So having argued that these efficient pseudorandom states exist, we're now going to argue that the exterior radiation prepared by the black hole is such an efficient pseudorandom state. So the setup going forwards will be this. So this is a circuit diagram in space-time with time always running upwards for us. And so we begin with some pure state of the matter. And this is just some unitary that encodes the black hole formation and evaporation process. So we look at some pure initial state of matter, and we let time evolve through the black hole unitary. And at some late time, we separate the system into 3 parts. There is going to be the early radiation. There is going to be the late outgoing mode B, which we will always take for simplicity just to be a single qubit, but the argument doesn't change very much if we consider a subset of any constant size. And there is going to be H, which is the remaining black hole, the part of the black hole that has yet to evaporate. And because the nature of this matter state is not going to be really relevant to us, we're always just going to call this state psi. So for us, psi is just always going to represent the overall state of the black hole and its external radiation at some constant time slice at late times. And for later purposes, we want to imagine that we can have some observer which interacts with the early radiation and perhaps perform unitaries on it. So we're going to introduce an ancillary system called O, representing an external observer, that's allowed to interact with the early radiation through some unitary, which we will always assume to be of low complexity. And by low complexity, again, I mean small with respect to the entropy of the remaining black hole. We're going to assume that the size of O itself, so size here is just the number of qubits in O. So these absolute values determine the number of qubits inside each subsystem. So we're going to assume that the size of O is going to be much smaller compared to the size of the remaining black hole. And this is our overall physical setup. We considered an old black hole with its external radiation and perhaps some external agent that's able to interact with the early radiation through some efficient process while being small compared to the black hole itself. So this is what we mean by having a computationally bounded adversary. So having this setup, let's argue now why we expect Hawking radiation to be in a pseudo-random state. And this argument in some sense goes back to one of the earlier arguments against the firewall paradox. So in their paper, Quantum Computation versus Firewalls, Patrick Hayden and Daniel Harlow argued that any experiment which witnesses firewalls must be by its nature exponentially complex in the entropy of the remaining black hole. And they argued that this was fundamentally unphysical because we should not trust actions which are of complexity exponential in the entropy of the remaining black hole. And they argued that, in fact, the firewall paradox itself should be seen as evidence that we have reached the limitations of effective field theory. They argue that effective field theory should be limited not just to low energies, as we're used to, but also to low complexities in order to achieve sensible results. And this is a point of view that we are going to endorse going forwards. So now, if we take this assumption to be valid, if we take the assumption that effective field theory should have limitations, not just in energy, but also in complexity, we can look at some of the original results of Hawking radiation through a new lens. So let's take a look at perhaps the most well-known feature of Hawking radiation, something that was derived by Hawking's original calculations for black hole evaporation, which is that Hawking radiation appears to be a perfectly thermal state. If we translate this statement to an effective field theory, which is only valid at low complexities, then we say that such a statement should only be trustworthy when seen from the lens of an observer with low complexity. So it's not really that Hawking radiation should appear thermal, but rather that Hawking radiation should appear thermal to any computationally bounded observer. And we're going to see that this modified statement has profound consequences on the structure of the black hole itself. So incidentally, whenever I think about these limitations of effective field theory, I'm always reminded of Clarke's third law. So Clarke was a science fiction writer who was perhaps best known by his laws of science fiction now. And the third law says that any sufficiently advanced technology is indistinguishable from magic. And this is the point of view that we basically take here. If we have an adversary which is allowed to perform operations of very high complexity, they're essentially performing magic to us. And such an adversary should not be trusted, and they should not be a part of our physical theory. And so we're going to examine the consequences of such a restriction going forwards. So to make precise exactly what it means for Hawking radiation to appear thermal only to low complexity observers, let's argue as follows. So let's psi of EDH, as before, denote the overall state of the black hole and exterior radiation. And we're going to let rho on EB denote the reduced state on the exterior radiation and the outgoing mode. And we're going to let sigma denote the maximally mixed state on the same system. we're going to make the following definition, because the fact that the state appears thermal to low complexity observers is basically saying that the state is pseudorandom. And so we're going to postulate this for the exterior Hawking radiation by saying that the state prepared by a black hole is pseudorandom when restricted onto the exterior subsystem. So we say that the state of the black hole is pseudorandom on the exterior radiation if there exists some constant alpha. We don't know what this constant is. There are recent arguments through, for example, the Python's lunch arguments and various arguments in holography that suggests that this alpha should be of order 1, perhaps something like a half or 2, something of reasonable size. But ultimately, we don't know what this value is, and we don't really care very much. All we require is that there is some constant greater than 0, which quantifies the degree of thermality of the state, basically. And so we're gonna say that the state is pseudorandom if, with respect to all 2 outcome measurements that you can perform on the exterior radiation, that the black hole state is indistinguishable from the maximally mixed state up to some exponential error parameterized by alpha in the remaining black hole. And so this pseudorandomness hypothesis can be seen as an axiomization of the thermality of Hawking radiation when restricted to these Harlow-Hayden type affected field theories. And so this is going to be the fundamental postulate going forwards. We're always going to assume that this is true for our black holes moving forwards. And we're going to see what consequences such a statement holds for these black holes. So the implications of pseudorandomness, we can show the following. So we can show that there exists an encoding of the exterior mode into the exterior radiation. Well, not quite the exterior radiation, it's really the remaining system. So the early radiation together with perhaps a part of the remaining black hole. But there exists some embedding of the interior modes, which are maximally entangled with the outgoing modes, into the Hilbert space of the remaining parts. Moreover, this encoding defines a quantum error correcting code, which we call the black hole code. And this code protects against all operations which can be performed by a computationally bounded observer, as I defined before. More specifically, this code corrects against all the channels acting on the early radiation, which has sufficiently small complexity, so polynomial in the entropy of the remaining black hole, and sufficiently small Krauss rank. So we require the Krauss rank to be sufficiently small compared to the entropy of the remaining black hole as well. And the takeaway from this is that through these conditions, you can show there exists a complete set of logical operators, which we call the ghost operators, that commutes with all of the correctable errors of the code. So they are effectively invisible to the exterior observer. And these ghost operators, we will see, serve as very concrete witnesses to both the smoothness of the event horizon and the preservation of the causal structure of the black hole. So all of this has been a little abstract so far, but there's a concrete model we can take which basically sums up everything we've done so far in a rather nice package. And so let's imagine a concrete scenario where some agent has access to a quantum device, but with limited memory. So the agent's able to program this device to perform one of a long list of unitaries to act on the early radiation. So we can model such an agent by a controlled unitary. So depending on the initial state of the agent, they will conditionally apply one of these unitaries onto the exterior radiation. And if we draw the corresponding circuit diagram, we have here the initial encoding for the black hole with the agent acting on the exterior radiation E through this controlled, through this overall controlled unitary, and preconditioned on the initial state of the agent, they will perform one of many unitaries acting on the early radiation. And when looking at this model, you can prove the following theorem. So let V be the black hole encoding I haven't defined, but that I've told you exists. And let U be the previous list of unitaries. So this could be a list of n unitaries, which are essentially arbitrary, but we require that n scale polynomially with the entropy of the remaining black hole, and that each unitary itself has a complexity which is polynomial in the entropy of the remaining black hole. And as always, I'm going to assume that the Pseudorandomness hypothesis on the black hole exterior state holds. So if all of these conditions are true, you can show that there exists a complete set of logical operators, L, for the black hole code, such that these following conditions hold. So the first condition says that each of these T is a logical operator for the black hole codes, and it's represented abstractly by this T tilde. So T tilde is the abstract logical operator, while T is the concrete representation of the code space. Moreover, these logical operators commute with all of the unitaries inside this set. So any unitary that this physical observer chooses to act on a radiation commutes when restricted onto the black hole subspace with all of these logical operators. And all of these relations are true in operator norm up to an exponentially small accuracy in the entropy of the remaining black hole. So there's a lot of information inside this theorem, but the physical message to take away is that the black hole interior is effectively protected from any action that a physically reasonable external agent can perform, so long as these actions are computationally limited. And this is basically the takeaway message we have. If you assume the pseudorandomness of the Hawking radiation, you can define natural error correcting codes, which makes the B tilde in E proposal a reasonable proposal in a physical sense.
Eugene, Eugene, why do you have to do this whole list of unitaries thing, this specific model, and
right?
Important?
Yeah. So to me, this is just a very concrete model for how we expect an external agent to interact with the unitary with the early radiation. So abstractly speaking, we just look at some channel which acts on the unitary, and O is just then a purifying space for that channel. But this feels somehow more physical, with a physical agent which interacts with the early radiation through some unitaries.
So you just want to allow the agent to do a mixture of unitaries instead of a fixed unitary. Okay.
That's right, yes. The point is that you can imagine jumping into the black hole and interacting with the radiation as you start to fall in. And you're only allowed to perform a limited number of operations because you just simply don't have that much computational power. And this theorem is saying that no matter what operations you choose, you can choose polynomially many of these operations, and you can choose them freely however you want to perform them. And no matter how you make this choice, there exists logical operators that commute with all of these choices, not just a single unitary, but all of these unitaries. So in a sense, it's a rather powerful statement when seen in this sort of lens.
Okay.
So this is essentially an overview of all the things we've done. So at this point, let me take an intermission, because now I want to give a sketch of the things I've said so far. And so let me just leave this slide up, which is just the technical definition of pseudorandomness here, while I get a drink of water. And we're going to be using this technical statement going forward. So maybe everyone can just refresh themselves on it.
So Eugene, by the way, it's 11:42.
Thank you. Yes, I have my clock now.
Okay.
I think we're good on time. So I won't be able to give proofs of most of the statements. I won't be even able to give very good sketches of most of the statements I've had. So everything I say here will be a little quick, and I'm going to forgive myself for this for two reasons, I guess. A, because all of the details are in the paper itself for anyone who is interested, and B, this talk is being recorded, so even if I do go a bit quickly, anyone who is interested can perhaps go back and just watch the videos more slowly to get at what I'm trying to say. So let's move forwards and see how the encoding can be defined and how the error correction happens. So the fundamental thing we have is a decoupling bound. And this is essentially an immediate consequence of the pseudorandomness hypothesis that we have. So let's consider some initial state of the black hole and the exterior observer. And we're going to act on this state with some polynomial-sized circuit acting on the early radiation. And we're going to let rho denote the state obtained by acting with the circuit onto this initial state. Now, the decoupling bound says that the reduced state of rho, when restricted to O and B, so O is the external agent, and B is the late outgoing mode, the reduced state, when restricted onto this subsystem, is exponentially close to being decoupled. Exponentially close in this factor of the remaining black hole and its difference with the size of the external agent. So this is why we require the agent to be very small compared to H. So to quantify this, we need this quantity to be small in order for our results to hold. So diagrammatically, if you look at the diagram on the right, this is the state rho. So we have the initial state of the black hole, and we act on it with some unitary performed by the agent. And then we trace away E, and we trace away H, and we're left with rho OB. Now, remember what the pseudorandomness hypothesis says. It says that with respect to measurements, we might as well replace the initial state of the black hole with the maximally mixed state. Making this replacement is effectively invisible to any low complexity measurement. And making this replacement of the initial states of the black hole with the maximally mixed states, you end up with the state here on the right. And by construction, these two states are indistinguishable with respect to, for example, any Pauli measurements you can perform on O and B. But if that's true, if they're indistinguishable with respect to any Pauli measurements, they must be close with respect to trace distance. So this shows that if the pseudorandomness hypothesis holds, that these two states are effectively close in trace distance. And the state on the right, of course, is decoupled by construction because it's a circuit which acts on E, and E and B are in the maximally mixed state, so they're decoupled by construction. And if you trace all the epsilons and deltas through this argument quantitatively, you end up with the bound 19, which we call the decoupling bound. And so going forwards, the decoupling bound is going to be key for everything that we do. So one consequence of the decoupling bound is it allows us to define a very natural code subspace associated with the black hole. And what we're going to essentially do is we're going to take the initial state of the black hole, and we're basically going to purify the system that represents the outgoing mode. So for people who like equations, this is the concrete definition of the encoding that we define. And for people who like diagrams, which I think is a lot clearer, this is what we mean by the action of the map V sub psi. So we just hit the leg B with some maximally entangled state, some EPR pair. And it's not clear that this actually forms an isometric embedding, but you can show, I won't bother trying to show this, but you can show that the coupling bound implies that this V psi is epsilon close in operator norm to some actual isometric embedding, and it's exponentially close in operator norm. And so we say that the subspace defined by this encoding is a quantum error correction code that we call the black hole code. And this makes concrete this B tilde in E proposal, because we're going to show and we're going to see that this abstract Hilbert space here, B tilde, effectively represents the modes of the entangled partner mode. So this represents the embedding of the entangled partner mode inside the interior into the exterior of the Hawking radiation, and perhaps a part of the remaining black hole itself. But this makes concrete what it means for the interior mode to be encoded within the exterior radiation. It's by means of this encoding map. So having identified a suitable code space, namely the image of this map inside the Hilbert space associated with E and H, we should now characterize its error correcting capabilities. And the way we do so is by using a very fundamental relation in quantum error correction, which is called the information disturbance trade-off. Now, the information disturbance trade-off basically says that the ability of a system to protect information is directly related to the ability of some environment to learn about that information. And you can make this quantifiable, you can make this concrete in a quantifiable way. But specifically, it says that if there's some physical process, some error, then that error is reversible if and only if the reference system that purifies the quantum error correcting code decouples from the environment of the error. So again, things I think are always more clear diagrammatically. So diagrammatically, the information disturbance trade-off can be depicted as follows. So you have here some error, which is correctable through some recovery channel. And by the information disturbance trade-off, this is equivalent to the diagram here on the right. So here we've purified the error channel into some unitary, and we've denoted the environment of the unitary to be F. Normally this would be E, but E is being used for our early radiation right now, so we're going to use F. And we're going to look at some reference state, which also purifies the code subspace. And so the information disturbance trade-off says that the error E is recoverable if and only if, after tracing out the system itself, the environment of the channel and the reference state of the code system is decoupled. So if you'll remember this diagram for a second, we can see that this is almost immediately applicable to the decoupling bound. Because if we try to write down the decoupling bound diagrammatically, we get this. So we have the initial state of the black hole, and the code subspace is being purified by the outgoing mode. We have the external agent here, which plays the role of the previous system F, the environment of the error. And when we trace away E and H, the decoupling bound says that the reduced system on O and B are decoupled up to exponential error. And this is basically an immediate translation into the information disturbance trade-off. And we can immediately conclude that this error channel acting on E here must be recoverable. And you'll note that O here, the system size of O, effectively quantifies the Krauss rank of such a channel. So the takeaway message here is that this shows that the black hole code corrects against all channels which are polynomial complex in H, in the sense that the purifying unitary has such complexity, and such that they have sufficiently small Krauss rank. So the concrete theorem is as follows. So let E be some channel on the early radiation with some purification U, and suppose that the decoupling bound holds for this channel. Basically assume that this channel has small complexity. Then this channel is epsilon correctable for this code, where epsilon is this exponentially suppressed error. So finally, let's talk a bit about ghost logical operators. And it becomes useful to recast the error correcting conditions of the black hole into an algebraic form. So one reason why this might be true is to look at the corresponding statement in effective field theory. So for example, let T sub B tilde be some operator which acts on the interior mode B tilde. By microcausality in effective field theory, any operator that some external agent can apply onto the early radiation should be expected to commute with the operator acting on the interior, simply because they should be causally separated. If we expect our black hole code to be a physically sensible thing, then the corresponding statement should also hold for our black hole code. And the corresponding statement is this. So the corresponding logical operator on TEH acting on the code subspace should satisfy the same relation when restricted to code subspace and all correctable errors. Namely, if we look at the action of T acting on the code subspace, or in this case, acting on the black hole state itself, we should expect it to commute with all correctable errors that some external agent can apply. So if you remember back to our concrete model, these external operations might be a bunch of unitaries that the agent has some choice in applying to the early radiation, and they should be, for causality to be preserved, our logical operators should be chosen in such a way that this relation always holds. And we call operators that satisfy such a relation to be ghost logical operators. And in a sense, the existence of these ghost logical operators is almost a necessary thing in order to preserve the causal structure of the black hole. And it turns out that these ghost operators actually do exist for basically any correctable quantum error correcting code, with respect to any correctable channel of quantum error correcting code. And the concrete theorem is as follows. So you can show that if you choose T to be any operator acting on the outgoing mode B, or if you remember back to our construction of our encoding, this is basically equivalent by purification to choosing any abstract logical operator. So for any choice of such an operator, you can show there exists a corresponding logical operator acting on the code subspace such that A, the action of this T on the exterior mode is equivalent up to exponential accuracy to the action of the logical operator acting on the exterior. And moreover, such an operator commutes with all the error operators that some computationally bounded exterior observer can apply onto the radiation, so long as these errors remain correctable, low complexity errors, basically. And equation 25, the first relation here, basically serves as a witness to the maximal entanglement between the outgoing mode and the encoded interior mode, because this is true for any operator you can choose acting on B. And this, as you can see, as we argued before, this was necessary for the existence of a smooth horizon, and this is certified by the existence of these logical ghost operators in this case. The second relation itself serves as a witness to microcausality. So the fact that these ghost logical operators commute with all errors means that the algebra of the encoded interior is effectively invisible to any exterior observer. They're causally separated. And this means that the encoded mode in the external radiation is basically a ghost. It's a ghost in the radiation, which is undetectable by any physically sensible adversary. And this shows that under these information theoretic assumptions, you can give a very concrete realization to this B tilde in E proposal that was sort of very confusing at first glance, and that all of these are, it conceptually makes sense. And that's basically everything that I have. So in conclusion, we find that this B tilde and E proposal for the firewall problem can be given reasonable meaning within the context of quantum information theory and quantum complexity. So under reasonable pseudorandom hypotheses, these black holes form natural error correcting codes against low complexity operations. These error correcting properties of black holes lead to the existence of ghost operators, which certify the preservation of geometry and causality. And moreover, we argue that operations with very large complexity can see violations, but we also argue that effective field theory should be limited in such a way that these are just not physically sensible operations. So I'm going to leave up this slide of open questions, of which there are very many, and I'm going to end my talk there.
All right, great. Thank you, Eugene.
Thank you.
So I guess we're trying to finish up before noon, but maybe there's time for one question. If someone has one, feel free to let us know. I guess while people think, so I mean, one thing I was sort of curious about from the beginning with the motivation, you were saying like how these sort of physical properties of locality and causality kind of turn into, is it correct to kind of say it becomes more of like a statistical phenomenon where like it could sort of be violated, but with exponentially small probability, or it's only that we could only detect it with exponentially small probability, assuming.
Well, if you're allowed to perform exponentially complicated tasks, then you can sort of see these as order one effects. But the point is really that causality, at least through our understanding, should not really be a statistical effect. It should be something that holds irregardless of whatever operation you can perform on it. And if we just naively embed the interior mode of the black hole into the exterior, then if we don't do this in a physically sensible way, then basically anyone can stroll along and play with the exterior radiation and see not just statistical, but very clear violations of causality. And this becomes very problematic for us because it means that many of the things that we think are true about general relativity and quantum field theory becomes false in this context.
All right. Okay, so we have one question here and then we'll probably wrap up. Alex asks, could you say a little more about what complexity means in the effective field theory sense?
So complexity in this sense is rather difficult, but it's basically the same sense that we always use. So basically we start with some simple state. For example, in effective field theory, we would typically take this to be the vacuum state. And we define the complexity of some state to just be the smallest number of gates which can prepare that state starting from our initial reference state. Now, it's very difficult to actually make sense of what this means inside quantum field theory, because it's not clear exactly what the gates of quantum field theory are. But if you choose some reasonable discretization, you can show that there can be notions of complexity which makes sense even in quantum field theory. So people have done this for, I think, free field theory. And generally, it's just believed, at least on a heuristic level, to make sense. But for our proposal here, we're really focused on limitations to just finite dimensional systems, to perhaps only degrees of freedom which are easily accessible to some external agent. So we really mean complexity in the usual sense of complexity when we talk about things here.
Okay. So I think I'm going to end the recording now, and we can all virtually thank Eugene. And then maybe if anyone wants to stick around, he could answer some
Sure, yeah.
questions one-on-one. But yeah, all right.